All right, before I get started, last call for questions. All right, so section 15 is going to be our last couple statistical tests. The name of section 15 is Statistical Power and ANOVA. ANOVA is one of the tests that we're going to be talking about. Just to look at what's in section 15, we have Statistical Power, which is actually something we talked about somewhere in I think it was in effect size. So we're talking a little bit more in depth into statistical power. However, statistical power, on Monday's study group, I'll actually walk through the process of determining your beta, which will make more sense on the next slide. So section 15, we have statistical power. We have a different kind of t-test from what we've seen so far. There is the KS test and ANOVA test. So altogether, we have 3 more tests that we're going to talk about, and then within those, we'll talk a little bit about the multiple comparisons problem in the context of doing an ANOVA test. So with this section, really the more important things will be like statistical power and Welch's t-test for doing A/B testing, which is going to be the next section. So those parts will be a little bit more important if you're interested in pursuing something that includes A/B testing. And then we'll see in a little bit that the KS test, the Kolmogorov-Smirnov test, and the ANOVA test are very specific kinds of tests that you would use in very specific instances that you might choose to do in your Mod 2 project, but not a necessity. So all right, let's get into these slides. So as I mentioned, we're going to talk about statistical power, Welch's t-test, the KS test, and ANOVA test. And these will be the last tests that we will introduce for the curriculum. And if we have a little bit more time, I know some of you have some questions about like translating formulas into code. And if we have time, I'll just like walk through some of the steps that I sort of take in my head to translate mathematical formulas into code. However, I will reiterate to say that that's not, the act of taking math formulas and turning that into code, not super important, but it is a good exercise for, you know, practicing Python and defining functions. But essentially all of these tests have like built-in one-liner functions in SciPy. So yeah. All right, let's get started. We have one slide on statistical power. Not too much because we're actually gonna do an A/B testing example next study group that will explicitly talk about how we determine beta, or determine the best threshold to maximize beta, sorry. All right, so power, I think we like touched on this a little bit in the last study group. Another definition of power is the probability of rejecting the null hypothesis when it is indeed false. So it is the opposite of a type 2 error. So up here we have one definition, 1 minus beta. So power is 1 minus beta, rejecting the null hypothesis when it is indeed false. So correctly rejecting the null hypothesis, which is the opposite of the probability of a type 2 error, which is failing to reject the null hypothesis when it is indeed false. And then here, power equals 1 is a perfect test that always correctly rejects the null hypothesis. And then this is the thing that we're going to go.
Last class we were supposed to talk about the beta. So would you be able to explain what exactly it is?
Yeah, it's a little hard to explain without context, but yeah, in the next section on Monday, we'll actually walk through that process of selecting, not really selecting beta, but determining a threshold to maximize power. So just know that beta, I think beta, a good thing to remember that beta is the probability of getting a type 2 error. I think that's something that's good to remember for now. And then Monday we'll like get deeper into like context, what it really means.
Okay.
Yeah, and this process, so this process after selecting alpha, you can typically determine a threshold to maximize power of a test. That is the process that we're going to actually walk through on Monday. Something that's kind of cool here. I don't know if I talked about, no, I don't think I talked about this on this past Monday, but this is something that's very cool. You typically want to maximize the power of your test. So this is like a cool interactive graph that shows you the relationship between your alpha, your sample size, and your effect size. And so you can like sort of play around and adjust these values, and you'll see where power is. So currently, with a significance level of 0.05, sample size of 20, effect size of 0.63, power is at 80 for this null and alternative hypothesis. This is something you can play around with. You can see as effect size gets bigger, the power is at 100%, gets bigger as well. Effect size gets smaller, power goes down. Sample size going up or down, so like the number of things in your sample can affect your power as well. Positive relationship, and significance. This looks really messy right now, but this is something that you can play around with. I think it'll definitely make a lot more sense after Monday. So that's just a little bit on power. Just to introduce, again, the concept of power. So this is just a fun resource that you can like play around and adjust different values to see how power is affected by all these other metrics. All right. So moving on from power, because I think the main bulk of this section is our other tests. So the next thing we're going to talk about is Welch's t-test. So we saw t-tests in the last couple sections. I think just the last section, we did like a 1 sample and a 2 sample t-test. So those were actually all students' t-tests. But typically when someone says a t-test, they are actually referring to a student's t-test. A more specific t-test is actually Welch's t-test. So the only difference between Welch's t-test is that it takes into account different sample sizes and unequal variances between samples. So an assumption that we didn't explicitly say for students' t-test, because it doesn't really make a huge difference. You'll see in one of the labs, they actually compare the result from a Welch's t and a student's t. But the only thing is, let me just stop my Slack real quick. The only thing is that Welch's t takes into account the two things, different sample sizes and unequal variances. So remember when we were calculating the t statistic? Here, the main thing is you see that there is the different variances of S1 and S2, where here SP is a combined variance for both. So Welch's t takes more into account their different variances. And then in the calculation of degrees of freedom, in the student's t-test, you would just take the total number of things in each sample and -2, whereas the degrees of freedom calculation for Welch's t, much more complicated. Good news, we never have to do these calculations because we know Python and there is a built-in function to do that, and it's actually in our labs. And I believe this is actually the one Welch's t is the one that we're going to be using on Monday to demonstrate an example of A/B testing. So if you remember, a 2 sample t-test the 2 sample t-test example that we did on this past Monday was comparing, I think, the effect of a blood pressure drug. So in a very similar concept, Welch's t will be actually looking at an example where I think it's a marketing or advertising example where we'll see if a marketing campaign actually had a good effect on like the number of clicks in a website. And that's the example we'll be walking through on Monday. That is also the example in your labs. And we'll actually be doing some coding for the first time in like a few weeks.
Any cheat sheets are available, like where we say that, okay, for any kind of test that we do, this is the formula that needs to be used in Python?
Yeah, so I'm actually working on that. I will send it out to your Slack channel. I'm actually gonna, after this study, I'm gonna actually put the formula from these tests that we're gonna talk about today, and then I'll send it out. I'll probably make like a PDF or a document or something and send it out to you all. It's just gonna be like a summary of all the tests that we talked about and like the specific conditions to consider for each one. Anything else? All right. So just an overview of the tests that we've seen so far. I think the two main questions that we look at is one sample different from the population? And that brings in our two one sample tests. So for example, a question that would be asked in this context is, does tutoring have an effect on the IQ of students? And I think we talked about this a week ago. And the two different kinds of tests that we've talked about are the one sample Z test and the one sample T test. And so the only difference between the two is when you know or don't know your population standard deviation. So if you know your population standard deviation, you'll use the Z test, and when you don't, you'll use the T test. And then are the second group of questions that you can be asked is, are two samples different from each other? So for example, A/B testing that we'll talk about next week, and drug effectiveness testing that we talked about earlier this week. You can use the two kinds of t-tests, the two kinds of two-sample t-tests, just the regular two-sample students t-test or the Welch's t-test. And the difference between the two are, in a regular two-sample students t-test, the samples are assumed to have the same size and variance. And for the Welch's t-test, they have different sizes and variance. And so these are the four tests that we've seen so far. So this kind of summarizes that.
One quick question. Any sample size is required, any amount? Let's say the population is 100. And is there any like percentage of minimum sample size required for like any kind of testing?
There isn't. There is actually a lab that talks about sampling and like good guidelines for sampling. I think it is it in the sampling? Here, I think it's in the sampling readings sort of talk about it first and then introduce the idea of sampling. And then in resampling methods, it talks about good practices for picking samples. That's a good question. All right, so these are the tests we've seen so far. The next two tests that we're gonna see, a little bit different. So first, we're gonna talk about the Kolmogorov-Smirnov test. So one thing that is similar amongst all these tests that we talked about before is there is actually an underlying normality assumption. There is the assumption that your population had a normal distribution. So now we're introducing the KS test that's actually testing whether your sample fits a normal distribution. And that's just important for, actually you might see this, you might end up using this in your Mod 2 projects because there are some things that you want to assume are normally distributed. But this KS test basically will test for how similar your sample is to a normal distribution. And what you do with that information could be useful for certain modeling techniques, could be useful for, I don't know, if you want to determining the validity of these tests, because these tests would be more valid if your samples come from a normal distribution, if that makes sense. All right, so how this works, it is basically comparing the CDF, the cumulative distribution function of your sample to the CDF of a normal distribution. So if you all remember, the PDF is the one that looks like a bell curve, but the CDF is the one that like goes from 0 to 1. So let me just like quickly Google an image of that. Let's see, normal distribution CDF. So the normal distribution CDF sort of looks like this. Sort of looks something with this shape. And so what you're doing in a KS test is you're comparing the CDF of your sample to the CDF of a normal distribution. So yeah. All right, so same steps. In any, this is still considered a statistical test. You still have the same steps involved. So you still have your hypotheses being set up. You still have to determine your alpha. You still have a test statistic. So in this case, the KS test for one sample KS test is also known as a goodness of fit test. And the hypotheses for this test is, the null hypothesis is that there is no difference between the distribution of a sample and a normal distribution. And so if you want your sample to be a normal distribution, you ideally do not want to reject the null hypothesis. And then your alternate hypothesis would be that there is a difference between the distribution of the sample and a normal distribution. So those are two hypotheses. As usual, we'll just set our alpha as 0.05. The new thing here is that our test statistic is a D statistic. And D is really just determined by the maximum difference between the CDF curves of your sample distribution and your normal distribution. So here, I'm actually not sure which line is the normal one and which line is your sample one, but imagine that, let's just assume that this second one, no, yeah, let's just assume that this like dotted line is the normal distribution and this solid line is your sample. Your D statistic is really just wherever you have the largest vertical distance between the two lines. And so after you calculate that largest distance, you will look up the D table. And so the D table sort of works similar to a T table where it gives you your critical values. So at 0.05, and let's just assume our sample has 20 items. So this is your level of confidence. This is the number of items in your sample. 0.05, so let's say we have 20 items. Your critical D would be 0.29. This table is pretty neat because if you have any sample size over 50, there's a general formula for your critical D value. So what you want to do is, if this test statistic D is greater than the critical D, you would reject the null hypothesis. Alternatively, if you just plug in your sample into the SciPy built-in function, it'll give you a p-value, and if your p-value is lower than 0.5, you can reject the null hypothesis as well. Questions on this? All right. I will say the KSS is not something that is as commonly used unless you want to verify some underlying assumption about your population, which I would say is not something that we do super often. But there are scenarios where if you want to see if something is from a normal distribution, sometimes that question might come up. You know that this test exists to check that it is normal. All right, so that was a one sample KS test. And the one sample KS test, just to summarize, it just checks if a sample is similar to a normal distribution. The two sample KS test is a little bit different. It just tests whether two samples were drawn from the same population or two identical populations. So that's like kind of the difference there. Hypotheses being null hypothesis, no difference between the two. Alternate being two distributions are different. They're actually very, very similar, these two tests, like the one sample and two sample KS tests. Same thing, you'll set your alpha, you'll set your D statistic, and in this case, rather than, the D statistic for a two sample test, each of these lines would be one of the samples, and then the D statistic would just be, again, the greatest vertical distance between the two lines. And then, again, you
can I interrupt for a second?
Sorry, what was that?
Yeah, let me interrupt for a second. What's the, could you go back to the other slide? Why does it say the same population or two identical populations? I mean, same and identical are synonymous.
Yeah, exactly. So whether it comes from one population, but whether you draw two samples from a single population, or let's just say you have two identical populations, like you just happen to have two populations that have, like you happen to have, like maybe you have two classes of 40 students and you want to look at their test scores and they just all happen to score like the same distribution of scores. And so that could be like, that's one of the scenarios where you would have two identical populations, if that makes sense. So it would be like drawing a sample from population A and drawing a sample from population B. So yeah, I hope that answered the question. Where was I? yeah, calculating the D statistic, very similar. Again, greatest vertical distance between the two curves. And the two sample D table, a little bit different, but it's just the number of things in each sample. It goes up to 12 on both ends here. And then you have these numbers over here. And for greater values of sample sizes, you have this general formula again. Pretty neat. You would basically multiply C of alpha, and C of alpha would just be this value. So if your alpha was 0.05, your C of alpha is 1.36. And then this combined formula of your N1 and N2. Let me just zoom in a little bit more. So for any sample size greater than 12 on each end, you would calculate your critical D, or actually approximate your critical D, by first taking the square root of the sum over the product of your ends multiplied by the C of alpha. And the C of alpha is determined by, again, you'll look up your critical value, usually 0.05, so it'll just be 1.36 multiplied by this square root of sum over product. And they have some examples here. And then very similar to the earlier one, if D is more than critical D, reject the null hypothesis or compare p-values. And that, again, also built into SciPy. Any questions about KS test?
Is the C of alpha like something like you would be expected to know for 0.05 or like in an interview setting? Not necessarily like obviously when you're just working. Okay, cool.
Not at all. Not at all. I would assume that in an interview, so I've actually never been asked a question about this, and I haven't heard of anyone being asked about this. But in an interview, if you're asked about like a KS test, very unlikely you would be talking about, if you're being asked verbally about any statistical test, and to interpret values, more likely you would interpret them by saying, if the p-value of whatever your test statistic is lower than critical, then you would reject null hypothesis. Usually you would phrase it like that rather than say, all right, I would calculate my critical and then compare it to my test statistic. But yeah, you definitely will not have to memorize like any numbers associated with critical values.
Okay, cool. Thank you.
You're welcome. Anything else? Cool. Awesome. So we can move on from the KS test. A lot of text on this slide, so I apologize on that, but we're going to introduce the ANOVA test here. The ANOVA test on the labs actually has really good examples of like working through and interpreting ANOVA tests. So I like that a lot. But ANOVA test basically compares group means with regards to a single variable. And so it looks to see if there is a significant difference between multiple groups. And this is usually for like 3 or more groups, because if you have 2 groups, you would just use like a 2-sample t-test. So yeah, it's just like doing many t-tests, but it gets rid of the multiple comparisons problem. I'll get back to this in a little bit, but an example of using the ANOVA test is this example that I have over here. Is there a difference between the mean GPAs of freshmen, sophomores, juniors, and seniors? So that's like an example question you use to compare the means of these 4 different subsets of students. To set up hypotheses really quickly, null hypothesis, there is no difference in the means. Alternate hypotheses, there is a difference in the means. As usual, you have your alpha at 0.05, and the test statistic here is a different statistic again, is the F statistic. And that is the formula, but it doesn't matter what that formula is, because I'll show you in the next slide what that would look like on when you code it out in Python. So is everyone okay with like the setting up of an ANOVA problem? I think this example should make it pretty clear of what we're comparing. It's basically like doing a 2-sample t-test, but with more groups. All right, if I have no questions on the setup, I would like to talk about the multiple comparisons problem. So some people will be like, why don't we just do a lot of different 2-sample t-tests? And why don't we just compare it that way, so we don't have to, bring in a different new statistic? That's because there's this multiple comparisons problem. So an example, so let's just say like an experiment that you do. So let's say the first comparison that you do yields a p-value of 0.03. And as we've learned, a p-value of 0.03 means that there's a 3% chance that your conclusion to reject the null hypothesis is spurious. And spurious is just another word for it's a coincidence or just happened by chance. So from that, the probability that you correctly rejected the null hypothesis is 0.97. And so let's say we're comparing like 100 groups. If we're doing this each time, and each time you have a p-value of 0.03, the probability of correctly rejecting the null hypothesis 100 times actually is only 0.04. So that means you actually have a very, very low chance of correctly rejecting all 100 null hypotheses. And that's kind of what the multiple comparisons problem gets to, is like you would have the product of all those type 1 errors. And so that's why this is what the ANOVA test takes care of. The ANOVA test takes care of this multiple comparisons problem.
So will this tell us like whether we should be rejecting the null hypothesis or not? Will this test tell us?
Yes, the ANOVA test, I'll show you in the next slide. It's pretty easy to tell whether you want to reject the null hypothesis or not. Yeah, that will be in the next slide. Something that I also wanted to show is that spurious, I don't know if anyone's heard the term spurious correlations, but there's this pretty fun website that actually shows things that, if anyone is familiar with the phrase like correlation is not causation, this website is just like a bunch of things that are correlated but have zero relationship with each other. And so that concept of being correlated but having no relationship with each other is sort of like kind of using like, is kind of a type 1 error, because it could be just coincidence that that you managed to reject your null hypothesis. But anyways, this is a fun read. For example, like the number of people who drowned by falling into a pool just happens to be correlated with films Nicolas Cage appeared in. It's just like a fun website to just find things that are randomly correlated. But I digress. Back to ANOVA, we're looking for a difference in the means of different groups. And our test statistic is F. That has like kind of a convoluted formula for calculating. I did stats in college. I never had to calculate this by hand either. So highly, highly doubt that you will ever be asked to. So this is one that is very, very easy to do in Python. This is a different library that we'll actually use in our Mod 2 project. And this is sort of a preview to our Mod 2 project, which is why I really wanted to talk about these particular lines of code. So this first cell is the input, this is the output. And this is actually the result of our ANOVA test. And so what you can see here is, actually, let me just introduce the data really quickly. You have a bunch of data. You have some sort of supplement and some sort of dosage. And I think this is like a tooth growth. This is a tooth growth CSV. So you have, I think, 2 different supplements. So if you see here, there is a supplement called VC and a supplement called OJ. And then you have different doses of each and how much it has encouraged tooth growth. I don't know what like these lengths are measured in, but basically a 0.5 dose in VC resulted in 4.2 tooth growth. And then similarly, a 2.0 dose of VC got a 23.6 growth. And then you have this OJ one, which basically, yeah, same thing, dosage, what kind of drug it was, tooth growth. So basically we want to see if there is a difference in the tooth growth for these 2 different ones. So really quickly, what this is that for each for each category. So here you can see that you're looking at which supplement it was and also which dose it was. How different are they? So for this, they actually calculate the F statistic for you. And then they give you a p-value. So this is actually probability. So it's a p-value. And this is basically like 4 to the power of negative 10 to the, it's 4 multiplied by 10 to the power of negative 4. So it's 0.00004. And this is really, really small because power to 10 to the power of negative 17. So these are very, very small p-values, which if you remember, you ideally want small p-values so they're not spurious, so that they are not by chance. And so therefore, we reject the null hypothesis and there is a difference in the means. So basically, what this is saying is that between the different supplements, there's a difference. And between the different dosages, there's also a difference. Does that make sense? So you'll see this exact thing in your ANOVA labs. I just wanted to explain this output and then also talk a little bit about what this code is really doing. So any questions about this output? Mm-hmm.
In the formula line there, it says len, and then that weird little squiggly like a tilde.
Yeah,
what does that symbol mean?
Yeah, I was actually just about to go back to that. But any questions about this output first? Like interpreting this. Basically all you need to know is you want to look for very small p-values to reject your null hypothesis.
So in this, like you will reject the C dose or you reject both of the?
So that's a good question. So basically, you could say that amongst the supplements, there is a difference in the tooth growth amounts for the different supplements. And there's a difference for different dosages. There's a difference in tooth growth for different dosages. So yes, you're rejecting the null hypothesis for both variables. All right. Okay. So now we're going to talk about this whole first chunk of like what this stuff is. So, sorry, excuse me. The way that ANOVA works in stats models, and stats models is a library that we use for statistical things as well. The way that ANOVA works in stats models is it actually first fits a linear regression and then looks at the deviation between the points in the linear regression. If anyone has like hit at our materials, our mod 2 project is actually going to be a linear regression. So this is actually something that you're going to end up doing, which is why I really wanted to talk about it. So how a linear regression works in stats models is first you have to define a formula. We're going to get way more into this in section 18, but basically this formula is constructed in, I would say, 2 parts. So first you have your dependent variable, which is the length, so your tooth growth. And then you have your independent variables. So basically you want to see how tooth growth is affected by the supplement that you take and the dose that you take. And basically the way that you construct the formula is literally just dependent variable, squiggly line, and then each of your independent variables. So this is just a formula for your linear regression. If anyone is familiar with linear regression, and you definitely do not have to be at this point, linear regressions have the format or the formula of like y equals to mx plus b. And so this would be like the y, length would be the y, and then the m would be each of these. And we'll definitely get way more into this, and there's 3 sections at the end of this mod dedicated to linear regression. So don't worry if this doesn't fully make sense now, but just know that this line is for linear regression. This is defining the formula of the linear regression. And if anyone is curious as to why this seems to be in a really weird and unfriendly format, this is actually the syntax of R. So if anyone's ever heard of the language R, a lot of data scientists, I would say like more in the past, use the R language to do like statistical analysis. And so this is actually R syntax, which is something that's very interesting. And OLS, what we're using here that we're fitting this linear regression model to. OLS stands for ordinary least squares, which is a linear regression, how we fit a linear regression. So this is the linear model. LM stands for linear model. And then from LM, we're trying to get the ANOVA of this linear model. So we extract the ANOVA from a linear model, and that's how we get this result. Any questions on that?
The LM is a standard word that we use? Like,
Actually, no, it isn't a standard. Some people call it like linreg for linear regression. Some people actually call it linear regression. LM, I do not think it's a standard.
so you have to define this as LM earlier and then use this here?
So LM is defined right here.
Oh, okay. Yeah, I missed it.
LM is defined right here, and then you're plugging this model into this ANOVA function. Yeah.
Mm-hmm.
I just wanted to like sort of explain each of these lines because the lab doesn't really talk about what each of these lines is, and I think it's important to know because this is what you will be doing in your Mod 2 project. Maybe not so much the ANOVA, maybe you end up doing an ANOVA, which is great if you do, but you will be doing at least this OLS formula dot fit in your Mod 2 projects. So this is just like a really quick preview of what you will be doing. And also to get you to seeing this formula.
I'm still curious to know, what is that squiggly line? Why isn't it an equal sign or something? And sometimes I see like a double one too in some of the formula in the modules.
Yeah, so it's kind of like you're trying to, so a squiggly line in math is more of like, I think an English translation to the squiggly line would be like represented by, is the way I like to think of it. And so you're trying to figure out how you can represent length as some combination of supplement and dose. I know that doesn't, I don't think that really answers the question, but like, it's just a symbol that they use for in R. And I personally don't really know R too well. But yeah, just wanted you guys to like see this before we get to linear regression. I actually think this is our last slide and we have 20 minutes left. Let's see. What else did I want to talk about? So we could go back and look into like an example of how you would translate a formula into code. So if we want, we can do that. But actually really quick, before we do anything else, I did want to talk about like the structure of Mod 2 and what to kind of expect. So I think I've said a bunch of times that like all these first few sections, sections 11 through 17, are more for you to just get exposure to the world of probability and statistics. But the stuff that we actually do for data science will actually only come in when we get to this linear regression, 18, 19, and 20. So what I'm gonna ask of you guys is that however you're progressing through these labs from 11 through 17, when we get to section 18, I think it's imperative that you all just like stop wherever you are. If you're like in the middle of section 14 or 15, stop there, skip 16, 17, and then just start at 18. Because I think it's really important that we follow along for 18, 19, 20. So if like by the time we get to 18, which is I think, what, next, let me take a look at the calendar real quick. Next Monday, yeah, on the 28th is when we start section 18. If you've only gone through like section 13 or 14, I would suggest to stop there and then skip to 18. Because anything that's stats related in 18, I will still bring back and call back. And like, if there's something that we don't understand in 18, 19, 20 that came from these previous sections, I will point back to like where is relevant. Reason being, 18 is where we really put everything together in context. And I definitely can see that, like I definitely understand sections 11 through 17 probably doesn't make a lot of sense for most of you people. Didn't make sense to me when I first saw this as well. So that's something to keep in mind. I will reiterate this when we get there, but just know that most important part of this mod will be 18, 19, 20. So I would highly recommend at least getting through section 14, because 12, 13, and 14 are where most of the things will come from that we see in 18, 19, 20. So this is just like a preview to the rest of the mod and like what's really important for this mod. Any questions on that? All right, cool. So I don't know if like, I don't know, you can like feel free to like emoji react, but I don't know how comfortable are people in like translating math to code. Yeah, all right. I'll just go through a really quick example of like, I guess this T statistic and how I would define this formula. Just so, let me just take this and copy it and put it closer to the formula. So I can like just walk through at least like my thought processes of like what I go through when turning a math formula into a function. So here we go. So this one's actually really nicely already sort of set up. So you already know what your inputs are going to be. And basically what we're going to do here is we're going to calculate the T statistic for these two samples, for any two samples. And A and B are going to be just two samples, hopefully as arrays. Oh, and something that I actually got as a question in a 101 is T statistic is equivalent to T score. The terms are interchangeable. All right, so calculating Welch's.
One quick question. So
Yeah.
what happens when there are multiple samples? So you just, like, here there is A and B.
Mhm.
So if there are like A to F samples, so you just distribute them just by separated by comma?
Well, Welch's T only works for two samples.
Okay.
Yeah, that's a good clarifying question. If you have more samples, you probably end up using an ANOVA. All right, I'll just talk through like what I think about when I'm trying to like create a function like this. And so ideally, this function will be able to take any list of, or any array of two samples. So I think you can see here that, yeah, each of these samples are arrays over here and the instant lengths. All right. So let's take a look at the math formula here. And what information we need from this. So here you can see that every time you see a subscript of 1, it means it's for the first sample, subscript of 2 is for the second sample. So it seems that what we need here is we need the sample means, we'll need the sample variances, and also the sample sizes. Usually when I see big math formulas, especially if they're in a fraction, I like to split them up as like numerator and denominator just because it makes things a little simpler. So I'll just start with that. Let's just like set that we have a numerator variable and a denominator variable. And then this just makes it a little bit simpler for me. So for the numerator, we know it's the sample mean of x1, sample mean of the first sample minus sample mean of the second sample. So as we know, A and B are each arrays for the respective samples. So it would just be A dot mean minus B dot mean. So that's pretty straightforward. This is, I think, where some people get kind of tripped up. So denominator, the main overarching thing that's happening in the denominator is you're taking an overall square root of something. And so if you want to break it down even further, you can just start with a numpy square root. Nope, that's not right. SQRT. Yeah, numpy square root. And we can call this maybe like, I don't know, let's call it variances. Not an accurate variable, but can't think of anything right now. And so that sort of breaks it down even more because we've already taken care of this square root. All we have to do is create this variable variances that comes in whatever is inside this this square root. And so I'll just break it down. Variances is equal to let's see, A dot standard deviation. I don't remember if this is the actual NumPy formula, but we can always look it up later. It's that divided by the length of A plus the same thing, B dot STD divided by length of B. And just to double check, I will Google NumPy standard deviation of sample. And oh, what do you know? It is STD. And then let's see. Yep, that seems to be right. I think there is a slight difference in the way that the standard deviation is calculated here. So I'm actually gonna really quickly look up the solutions, which is something that there is no shame in doing. I'm gonna look up and just make sure that the standard deviation formula is correct. And so you can see that, oh, it's actually variance. Sorry, my bad. It's actually variance with the degrees of freedom equals to 1. And so, all right, basically you can see that we've sort of broken it down the same way. Let's just make it the right one. So it's not standard deviation, it's actually variance. And degrees of freedom equals to 1. Let's replace this as well. And when you return it, you can really put it all together, or you can put it all together separately before the return statement, but you can just do numerator divided by denominator. And that is done. So let me just run these really quickly and run this. And you can see that you have your t-value, t-statistic. Did that clarify anything for anyone? There are a lot of these like code out a function to write your t-statistic, to calculate your t-statistic from scratch. As I mentioned earlier, it's really not something that you need to be able to do. Like one, you definitely don't need to memorize any formulas. Two, all of these formulas are already built in. It is a good form of Python practice. So however comfortable you feel with Python, yeah, whether you do that or whether you do these parts of the lab or not, really depends on how comfortable you are with Python at this point. But yeah, that's all I had planned for today. Any questions?
Why for the variance do you have to do degree of freedom equal to 1?
It has to do with the specific way that NumPy has it set up. So let me just look it up in the docs really quick. NumPy variance. Let's see. NumPy variance, they say degrees of freedom. So by default, degrees of freedom is 0, or delta degrees of freedom. So delta degrees of freedom basically is the change in your, is however you want to minus away from n. And because it's a sample, not the population, you always divide by n minus 1. There's a really, really good StatQuest video saying why you want to divide by n minus 1. Let me just look it up. StatQuest, n minus 1. Maybe that will give me the result. But yeah, why dividing by n underestimates the variance. That's a really, really good video in explaining why you always want to divide by n minus 1. And why you always want to use the var DDOF equals to 1. But yeah, this guy explains it infinitely better than I could ever try to explain it. Any other questions? Awesome. Well, as usual, any questions you have, feel free to Slack me as and when. If not, have a good evening, everybody, and I will see you all at your one-on-ones. All right. Bye, everybody.